Okay, so we did on Monday, we did the quick redox reactions, assigning oxidation states, balancing redox reactions. And today we're going to talk about voltaic cells. So this is actually new stuff. So electrical current, if you didn't know, is a flow of electric charge, more or less, through a wire or ions through a solution. Um, and redox reactions can generate electrical current because zinc, in this reaction where zinc's reacting with copper, zinc has a greater tendency to lose electrons, and so it gives all of its electrons to the copper spontaneously. The way that we generate electricity from this is by forcing them to transfer those electrons through the wire. And where are the electrons lost? The anode. They're lost at the anode, which we'll get to. Right? So you could take copper solution, and if you put a zinc strip in it, eventually you'll get all of this black nastiness on the outside of it, which is the copper coming out of the solution and turning into a solid as the zinc is losing those electrons. That's, well, can be useful, but not for generating electricity. So if you separate those zinc atoms and copper ions from each other and then use a wire, that's how we get electrochemical cells. So we've got chemistry that's driving the motion of the electrons through the wire. Voltaic cells, which is where we're producing that electrical current, and then electrolytic cells, which consume electricity to drive a non-spontaneous chemical reaction. One way that you can do that is electroplating. So you pass electricity, force electricity into something, and then that will turn some metal ion in the solution back into the solid metal, but on the surface of, I don't know, a metal plate. So you could use this with dissolved gold, and you could gold plate things that way. Small tangent, the way that they used to plate things in gold, though, was not with electrochemistry. They would mix it with mercury, because gold dissolves in mercury, and then you would paint it onto stuff, and then you would hit it with usually a torch, right? You just heat it up, the mercury boils, and it leaves the gold behind. One place where they used to do that a lot was in making fancy hats, which is why the Hatter is mad. So the Mad Hatter is crazy because he's got mercury poisoning. It's super dangerous. I wish I could say that nobody does it anymore, but I've seen videos on Reddit, third world countries, where they still do, what's it called? The flame gilding. Yeah, not healthy stuff. Anyways, electrolytically doing that is safer. So this is our electrochemical cell, and we have an anode, which is where electrons are lost, as I have forced you to know with that great song. So our electrodes are these metal strips. The reactions actually take place at the surfaces of these metal strips. And then to separate these things, we've put them into two separate solutions. So on the left, we've got a zinc and zinc nitrate solution. So we've got zinc and its zinc ions. And then on the other side, we've got copper and copper nitrate. And you could pass electricity, like you could do this reaction, but if you do it without the salt bridge, eventually it stops. Because on this side, we're going to be we're going to be producing these zinc ions. And so we'll get a buildup of positive charge. And then on the right side, we'll be using up the copper ions. And so we'll actually have more negative charges than positive charges. And the reaction would eventually stop. So what you do is you put the salt bridge in between, which lets the ions pass through. So you get potassium in your nitrate, moving to balance those ions out. Like, is this the same? Yeah, and so connecting these with the wire, then spontaneously electrons will flow because the zinc is being oxidized. Oxidation is loss. Oxidation takes place at the anode because the anode is where electrons are lost. And so we got electrons being lost. So zinc turning into the zinc 2+, and then giving up those electrons. Now those electrons have to travel through the wire, through the load, which is never understood why that was on fire, but it rhymes. Then in the cathode, those extra electrons get picked up by copper ions, and they turn into copper solid. So reduction takes place at the cathode. So these might come up a little bit. Specifically in Alex. I guess maybe we could calculate at some point like the number of electrons that actually get transferred for one of these things, and we would do it using these. So an amp is a unit of electrical current. High amps is what will kill you if you get electrocuted. If it's something with very, very low amps, high voltage, that's usually fine. If it's enough voltage and high amps, you're done. That's what pops circuit breakers. Amps are dangerous. Volts can be dangerous. Coulomb is the unit of electrical charge. And if we look here, we can break down the definition of amp, which is actually coulombs per second. And so then so a coulomb is 6.242 times 10 to the 18 electrons. And an amp is that many electrons per second. So it's kind of like water, although water is a very, it's a so-so analogy. Electrical current is driven by a potential difference. So potential is not like you have the potential to become whatever you want, like great potential. We're talking about a difference in energy between both sides of the reaction. And so that's always going to be relative from one thing to another. What is the potential difference essentially in energy? Per coulomb. So joules per coulomb, we can see if we break down a volt, which is our measure or our unit for potential difference, is joules per coulomb. And if a coulomb is a number of electrons, then this is the amount of energy different two things are per coulomb of electrons. So you calculate this as, by moving one electron from one place to another, how much energy difference is there between the electron's starting place and its ending place? So to continue with the water analogy, this is like a height difference between the two systems. The water will flow from a higher place to a lower place. So the mechanical potential energy is the amount of water that flows from the high place to the low place. So this is the amount of energy, and instead of water, it's per electrons. We're going to see a lot of volts. So large potential difference then corresponds to a large difference in charge between two electrodes. So again, basically, if the electrons stay in the starting place, they've got really high energy. If they go to the new place and they've got really low energy, then that would be a big potential difference. Another way to think of this, though, is electromotive force. So instead of thinking this as just the difference in energy, it's how much the electrons are being pushed. It's kind of like water pressure. If you have really high water pressure, then the water comes out really fast. I think it'd be kind of, if we continue with the water analogy, kind of analogous to gravity. So the potential energy difference in water in a high place and water in a low place is driven by gravity. Right? Otherwise, they wouldn't flow. So when we calculate this for a cell, the electrical chemical cell is the whole system, which is, okay, I thought there was going to be a picture. Almost got to it, right? This is an electrochemical cell. That's the whole thing. And if we want to calculate a potential difference, right, what is the difference in energy per coulomb of electrons from the anode going to the cathode? So how much energy can I get per coulomb of electron as I flow through this system? It's going to depend on both sides of the cell and the difference between those sides of the cell. So the reason our previous one flowed is because zinc has a greater potential to lose electrons than copper. So zinc loses its electrons, copper gains those electrons. But if I swap any of those out, then that changes the potential difference. So if I used magnesium instead of zinc, Magnesium has a greater potential, I believe, greater potential to lose electrons. So then our potential difference would be higher. We could use more and more reactive metals to lose those electrons and get higher cell potentials. This is, I meant to look this up to make sure that I was 100% on this. But this is why like batteries are they like 1.5 volts? And there's like the standard voltage for batteries. It's because the original batteries were based on an electrochemical cell with a voltage difference of 1.5 volts. Because batteries, remember, batteries, pretty much all batteries, excluding capacitors, are chemical or bottled chemical reactions that we force to go through a wire. They're bottled electrochemical cells. So like a nickel cadmium battery has nickel and cadmium in it. Those are both sides of the cell. And the cell potential is the difference in energy from one to the other. And so that really set what the original batteries were at like 1.5 volts. If I'm remembering that correctly, that seems slightly off for some reason. But that's also the problem with making new rechargeable batteries. Because you make like lithium ion rechargeable batteries, the lithium ion cell potential is different. And so then you have to put in a bunch of electronics to make it 1.5 volts because we still want to be able to use that battery in all of the things that we could before. Anyways, adds complications because we're not changing the size of batteries. Right, okay, so relative difference, high positive cell potential, yep, high oxidation potential versus low. It does depend on concentrations and temperature, which we'll get to at the end of this chapter. But just like with standard enthalpy, standard entropy, we have a standard cell potential, which, oh yeah, I tried to do an experiment with somebody at Friday Night Lab related to the last chapter. It didn't end up working, and because of a bunch of things that I had forgotten about. But ChatGPT had a great turn of phrase for these standard states that I just really enjoyed. So we talk about standard conditions, right? Standard conditions is everything at 1 atmosphere, everything at 1 molar, everything at 25 degrees C. And ChatGPT says standard states are a very particular kind of fiction. It is, in a sense, an imaginary world where everything just is what it's supposed to be and doesn't change. Because as soon as anything changes, then it's no longer that standard state. They're useful because they give us a lot of information. Because if we know, like, oh, this standard state, we can do that for some system, then we can predict how other systems will deviate from that when they're not at standard states. So a very particular kind of fiction. This is one of those imaginary worlds that we use to make calculations easier. So our standard cell potential, so using that same naught or 0, is at 1 molar or pressures of 1 atmosphere. Which statement best captures the difference between volt and amps? Yeah, A. Volt is potential energy, amp is the flow of electrons. So the zinc copper cell that we talked about before has a standard cell potential of positive 1.10 volts. Meaning that as this reaction proceeds, or if this reaction proceeds forward, then there's a potential energy difference per electron of 1.1 volts, 1.1 joules per coulomb of electrons transferred. Which is really saying that over here, the electrons are in a higher energy. This is E. Again, reactants going to products. We're going down to some lower energy. If we replace zinc with a different metal, so we go to nickel here, you can see the cell potential is now only 0.62 volts. So if we've reduced the potential difference. And that's because nickel just has less potential to be oxidized, or less tendency to be oxidized, or it's not as easy to oxidize. So for electrochemistry, the standard cell potential, so E cell, positive is spontaneous. I think you can think about this as like the amount of energy that you get out going from reactants to products. So if I get a positive E cell, that means that I've gone from a higher energy to a lower energy, and there's this amount of energy per coulomb of electron that gets released, or could potentially be captured. So that means that if E cell is negative, that means in the forward direction, I actually have to put energy in order to make that reaction happen in that direction, because this is tied to the direction that the reaction is written. So if I flip these, then I flip the sign, because now we're going in the opposite direction, and it would take energy input to go backwards. So if this is like these two beakers of water connected by a tube in a voltaic cell, which direction do electrons flow? They go from high to low, cathode to anode, from lower potential to higher potential. They go from high to low. And B can't be true, because where are the electrons lost? Anode. Start at the anode. Electrons are lost there. Don't forget it. So this would actually go this way. Start at the anode, they go to the cathode, so that's backwards. So oxidation occurs at the anode. Oxidation is lost. We start at the anode, electrons are lost there. This is why this is so important. Now you can never forget. You have no excuses. Oxidation occurs at the anode. Reduction then occurs at the cathode. Oh shoot, somebody gave me a better mnemonic for remembering these. But the red cat, reduction at the cathode. Oxidation occurs at the anode. I know they both start with vowels, but oil rig is oxidation is loss, reduction is gain, which is why if you could remember that part and you can remember the song, start at the anode, electrons are lost there. So electrons are lost there, and oxidation is loss. Oil from oil rig. Literally going through these slides, that's how I remembered it every time. Start at the anode, electrons are lost there. Oxidation is loss. Oxidation at the anode. And then if that's happening at the anode, then the opposite has to happen at the cathode. So, oh yeah, the following only works for voltaic cells. The anode is more negatively charged. Anions are negative. The cathode is positively charged. Cathode are positive because it's a cat paw. The first one's more consistent. And then electrons flow from the anode to the cathode. I guess, yeah, that only works for voltaic cells. We will talk about, wow, the other one. Well, electrolytic cells. That's what it was. Kept getting stuck on electron. So voltaic cells, when we're generating electricity again, electrons flow from the anode to the cathode. If we didn't have the salt bridge, which I mentioned before, the salt bridge allows counter ions to flow between the cells without the solutions mixing. So an inverted U-shaped tube containing a strong electrolyte connects the two half cells. And there's like a spongy kind of plug at the end, which allows the ions to transfer. And unless you used a really fancy one, eventually the positive and negative, or like the cations from the opposite solutions would make their way through the salt bridge. But since you're not actively mixing them, that's going to be crazy slow. It's just important that we're allowing some ions to flow so that we can neutralize the charges that build up. So to look at it again, we've got our voltaic cell. We have our anode where we're losing electrons. They go through the wire, set the load on fire, or through the load on fire. I always thought it was set the load on fire. Into the cathode, and then because we are here creating zinc ions on the anode cell, and then we're using up cations in the cathode cell, then we need to swap these ions to make up for those charge differences. Otherwise, the reaction does stop. So if we had to write out those huge diagrams every single time, it'd be really inconvenient. So instead, we have electrochemical cell notation, where we use vertical lines. Well, we use the single vertical line represents a boundary between two phases. So for the zinc anode, which is solid, it's in a solution of zinc ions. So the reaction can only really happen at the boundary of those two. And so we use a vertical line to say like two different phases. The double line represents the salt bridge, which separates your two cells. And on the other side, I've got a single line. Sometimes if you get well, we will see maybe today, a reaction that has, well, both of the ions are in solution. So it goes from a manganese +7 to a manganese +2. And those are both aqueous in the solution. So like if all the principal species in a half reaction are aqueous, then you use an inert electrode such as platinum, PT. I probably should have deleted that. Oh yeah, no, there was this next one, right? Okay, cool. So the half reactions here, it's already balanced. But what's being oxidized? Bless you. Yeah, other way. Yeah. Yeah. So iron's going from 0 and it's going to +2. So that's the oxidation. So we can keep this balanced. 5 iron, solid. 5 iron, 2 plus 10 electrons. And then the thing that's being reduced, yeah, is the manganese. -8, So this is plus 7. This is plus 2. Just to be complete, the oxygens. Well, I guess I should say these are still minus 2. This is plus 1 for each. So then in the reduction, oh, well, it has to be 10 electrons. So how did I know how many electrons for either of them? For the iron one, yeah, oxidation number times the coefficient means that that side has a 10 plus charge. So then I need 10 electrons to balance it with the other side. Because this is 0. Without the electrons, this side was a positive 10. So 10 electrons brings that back to 0. And then when I did the second one, I saw that my first half reaction had 10 electrons, so that my second half reaction, as long as I'm writing everything in with coefficients, has to also be 10. But it should be the same logic where this side is 16 plus, and then 2 minus, so that would be 14, positive 14. This side's positive 4. So positive 14, positive 4, which means 10 electrons brings it to positive 4 on both sides. This is balancing the charges. And then like on this one, I knew, I guess, how did I know that the water and the hydrogen have to go with the manganese? Yeah, permanganate has oxygen in it. So it means that the waters have to be part of that reaction. It'd be more, like, it could be more complicated. Because honestly, it would be easier to do this just as, like, if you had to balance it first, then it'd be easier to write the half reactions because they wouldn't have everything in them. But then our line notation should reflect our two half reactions. And as long as it's a voltaic cell, this side will be oxidation. So I have my iron going to iron and electrons, which means it's losing those electrons. So it's oxidation, and then this is the reduction. And which one is the, oh, right, yeah. Which one is the anode? Yeah. The oxidation. That's my anode, and then the other side has to be the cathode. And this is that example that I mentioned, right? So we've got iron solid, and we've got iron 2 plus, which is in the solution, aqueous. In the other half reaction at the cathode, permanganate is aqueous, manganese is also aqueous. And even though hydrogen's not really doing anything, it is in the solution, another ion that's in the solution. So we include it here, aqueous. And then because we need some solid interface, that's where we use the platinum electrode at the end. I suppose you could also use carbon. Graphite electrode. Okay. Cell notation. So then as a diagram, this would look something like this, where we have iron and the iron electrode on the left side. And then on the right, in the right cell, we've got the cathode, which here the cathode is platinum. And then in the solution, I've got hydrogen, permanganate, and manganese. Cool. So, standard electrode potentials. Is it in the next slide? Oh yeah, it is. Okay. So if we know what the E cell is, we can tell if a reaction is going to be spontaneous. And for any electrochemical reaction or any voltaic cell that we create, it's going to depend on the cathode and the anode of the cathode, and the difference in potential energy between those. So we need to have a way to write down that potential, that standard potential, for half cells. The problem is that it's unlike the water analogy, where I've got like one with high potential energy and one with low. I can just look at the water and see, oh yeah, the water's higher there. Can't determine the electrical potential energy of something just by looking at it. And this is another one of those things where it's like, we also can't really quantify the absolute amount of energy that something has, just like we can't quantify the absolute entropy or the absolute enthalpy of things. So we set something to be the standard because, like those other functions, this is also a state function. So the only thing that matters is where we start and where we end. And as long as we can compare those two, we can calculate a potential difference for the cell. And either we try to get the best thing or the most convenient thing to compare everything to. So for electrochemical cells, for our half cell potentials, oh, I guess I got a little ahead. So it can't determine for an individual cell, so we compare it to the same standard electrode half cell. And then, so that standard electrode is the standard hydrogen electrode. She is the usual reference. I don't remember what this was supposed to be. So the standard hydrogen electrode just uses hydrogen gas at 1 atmosphere and a solution of hydrochloric acid with 1 molar concentration. And we say that standard electrode, which is a relatively easy electrode to make, is 0. And so we're not really comparing to any absolute value. We're just saying when you connect 1/2 cell to this hydrogen cell, the standard hydrogen cell, standard hydrogen electrode, what's the voltage then? Positive, negative, but we can measure those voltages relative to this one, and then measure those voltages, or use those voltages to compare other things. In my mind, it's like a fighter tier list. There's like a bracket, and everybody fights hydrogen first, and then depending on how hard they beat hydrogen or get beat up by hydrogen, that determines where they stand in the rankings. And so if something gets beat up by hydrogen and it reacts with something that beat hydrogen up, then we can make a prediction about how those two things would fight. And these are all tabulated as reductions. So oxidation happens at the anode. We're essentially saying, if all of these things were the cathode, what is their voltage? Hydrogen is my anode. Everything else is the cathode. What's the voltage for those reactions? And we're going to see that some of them are negative, because sometimes the reaction doesn't flow from the anode to the cathode, but it would flow from the cathode back to the anode. So really the negative sign here is just telling us the direction of the reaction. So in this example, we've got the zinc hooked up to my standard hydrogen electrode. And when we do that, we get a positive voltage. This is positive 0.76 volts. To calculate E cell, it's always cathode minus anode. And this also kind of follows, like when I write out this whole reaction, it would be a zinc plus 2H plus goes to zinc 2 plus H2. We're kind of doing products minus reactants. So kind of like how Gibbs free, Gibbs free energy, enthalpy, entropy, they're all products minus reactants. This is still kind of products minus reactants. Not quite, but it's a parallel. What we're really saying is the electrons, what's the energy of the electrons at the cathode compared to the energy of the electrons at the anode? And that gives us the potential or the difference across those two. So for this one, our measured cell potential is positive 0.76. And when we write that as the reduction potential, because our standard potentials are all for the reduction, and reduction is gain, then really it's for the reversed reaction, and it's negative 0.76 volts. Because when we do this calculation and we do cathode, they didn't write out the anode here, but it writes cathode minus anode. It's my cathode, which is 0. It's actually exactly 0, minus negative 0.76 volts. So that equals an E cell, which is a positive 0.76. So compared to hydrogen, zinc wants to get rid of its electrons more. And so when I pair zinc as the anode with hydrogen as the cathode, this reaction is spontaneous. And when we're talking about, this is specifically for voltaic cells, you can think of this more negative electrode potential. That means greater potential energy because the negative charge repels electrons. So if electrons have negative charge and my voltage is negative, then those electrons want to move away from that reaction. And if it gets more negative, they want to move away even more. Not exactly what's happening, but it can help keep things straight. If we switch out the zinc for copper, and again, copper here is the anode, the measured E cell is now negative 0.34. So my overall E cell is negative 0.34, which is going to equal whatever, oh, my cathode's always 0, minus whatever the voltage of copper is. So in rearranging these, we get the potential of copper is equal to a positive 0.34 volts. So what we're seeing here is that copper is not as good at getting rid of its electrons as hydrogen is. So as written, with copper as the anode, that reaction is not going to be spontaneous. It'll be spontaneous in the other direction, which is why when we pair copper with zinc, which we saw has a negative cell potential, so negative 0.76, it's much better at getting rid of its electrons. Copper lost to hydrogen and took electrons. So then if zinc was able to give its electrons to hydrogen, hydrogen would be able to give its electrons to copper, then zinc should be able to give its electrons to copper. And in a sense, we've got these voltages kind of like pushing against each other, and whichever one's stronger ends up winning, and the flow goes in the direction of the stronger half cell, the stronger half cell. So similar to if the electrode is negative, then it tends to repel. So the zinc electrode is negative, so it tends to repel electrons toward the standard hydrogen electrode. For copper, the electrode is positive, so it tends to draw electrons away from the standard hydrogen electrode. So again, we're comparing everything to hydrogen, and then we write all of those as reduction potentials. And mostly that's just for consistency. If we have to write all of the values down, might as well write them down all the same way. Consistency and convention. So actually, if we wanted to compare these two, yeah. So which copper or zinc, which one's the better anode? So what happens at the anode? Electrons are lost there. Starts at the anode. Electrons are lost there. So which one of these is better at losing electrons? You can use the sign of the voltage to figure out if it's better at losing electrons or better at gaining electrons. So zinc here is more negative. Zinc is better at losing electrons. You can think of those electrons being repelled from the negative. So the better anode would be zinc. The better cathode is copper. And so we would expect this reaction to be spontaneous if zinc is being oxidized and copper is being reduced. Another way, oh wait, we're like out of time. Dang it. All right, I'm gonna try this real fast. But another way to think of this is that when you are looking at these potentials, they're all going to be for reductions. But for the redox reaction, we have to have one that's being reduced and one that's being oxidized. The spontaneous version will end up with a positive E cell. So these are both written for reductions. Reduction, reduction. But if I rewrite this reaction for zinc as zinc 2 plus, or sorry, that's the same way. Zinc solid plus, or not plus, goes to zinc 2 plus 2E minus. Now that's the oxidation reaction. the E cell, or the E half reaction, right, the standard potential for this, the sign changes. Now it's positive 0.76. Now when I add that to copper, they just add together and I get a positive voltage. That would be the spontaneous reaction. The standard way of doing this, where you do cathode minus anode, has the negative built in. So like here, I flipped this to be the oxidation reaction. But when you do cathode minus anode, so I wrote it as the oxidation and I flipped the sign. But if you do cathode minus anode, you end up with the same thing because the negative flips the sign on the anode. All right. I now have office hours, so if you have questions about the exam, if you can't make it to those office hours, it's downstairs in 115, JM 115, study the lecture worksheet for the last chapter. I will be using that to write the exam.